circuit rules, or circuits rule. This is Kirchhoff's first law. At any junction in a circuit, junction being here, the total current leaving the circuit is equal to the total current entering the junction. Looking at this diagram here, we've got 0.5 amps going in and 1.5 amps going out. What must be happening here? Well, you've got more current going out than you've got going in, so this must be 1 amp going into the junction. This rule follows from the fact that electric charge is always conserved, and you might want to have a read about that in your textbook. Okay, so another current rule, this time in series circuits. The current entering a component is the same as the current leaving a component. So same current here. In these circuits, the ammeters have very little resistance, and so they don't affect the current in the circuit. If we've got more bulbs or components in the circuit, the overall current will go down, but you'll find that the current through each one at any point in this circuit is the same. Now let's have a look at potential difference, and this is in series circuits. For two or more components in series, the total potential difference across all of the components is equal to the sum of the potential differences across each component. The battery opposite gives each coulomb of charge energy. In this case, V0 volts per coulomb. This energy is lost in 3 stages, V1, V2 and V3. Therefore, the total potential difference across the circuit, V0, is equal to V1 plus V2 plus V3. Potential difference in parallel. Potential difference across components in parallel is the same. In this circuit, after passing through the variable resistor, the charge carriers, electrons, have energy per coulomb which is equal to V0 minus V1. So the V0 is the potential difference across the battery, and V1 is the potential difference across the variable resistor. The charge carriers then pass through both of the resistors in parallel. The same amount of energy per coulomb, V2, is delivered to both resistors. Hence the PD across both parallel resistors is the same and equals V2. So there's V2 across this resistor and V2 across this resistor. Same potential difference. When talking about the voltage of the battery, we generally use the term EMF, electromotive force. And this is the voltage produced inside the battery. And then we talk about the potential difference across each component. This is the same as the voltage across each component. In this circuit loop, the variable resistor uses up 3 joules per coulomb, which is 3 volts, and the bulb uses 6 joules per coulomb, which is 6 volts. Remember, 1 volt is 1 joule per coulomb. So in general, we say that the sum of the EMFs is equal to the sum of the PDs. So if we had more cells at the top here, you'd add those up and they would equal the sum of the PDs across each component. And this is known as Kirchhoff's second law. So what do we do with resistors? Well, let's have a look at resistors in series. Here we've got two resistors. We've got I flowing through R1 and then R2, and you've got the same current coming out. What do we know about the potential difference? Well, we know in series they add up. Okay. We also know that V equals IR. So here we can put a statement for R total. So what's the total resistance of these two, RT, will be I times R1 plus I times R2. What can we do with the I's? We can cancel those off, and what we end up with then is the total resistance for series resistors is simply, you just add them up. And there we go. If it's more than two resistors, it's R1 plus R2 plus R3, etc. So here we have two resistors in parallel. And remember from Kirchhoff's first law, the current going in will add up to the current coming out of that junction. So now we have an equation where the currents add up. Current, of course, is V over R. Okay, and for each of those resistors, the voltage is the same. So we have V over R1 plus V over R2. Now what we're interested in finding out is the total resistance again. So here we have V over R total T. Okay. Now this time we can cancel the V's and they end up as a 1, don't they? Okay, so we now have 1 over R total equals 1 over R1 plus 1 over R2. And this is where you've got to be careful with your maths. If there's more than two resistors, it would be 1 over R1 plus 1 over R2 plus 1 over R3, etc. But always remember at the end, the answer, you've got to do 1 over that. Try it with some numbers. So, to summarise, in series, the current is the same through all of those R1, R2 and R3. Voltages add up. And the resistances, that's our total, add up. For parallel, the voltage is the same across each component. The current going into a junction equals the sum of the currents going out. In fact, the sum of the currents going in equals the sum of the currents going out. And working out your total resistance, you need to use this equation. And now it's time for you to have a practice.